Okay, welcome to the Denver Erlang and Elixir meetup. This is for Monday, April 7th, 2025. The meetup tonight is sponsored by Praxis.io, which is the first and only security platform that has full Elixir support. So if your business is using Elixir and you need help with security, definitely check out Praxis.io. So our main event for tonight, Marcos is going to be giving a talk about learning Axon with a tic-tac-toe game. I'm really looking forward to this. I'm actually very curious how Axon works, and I love talks with real examples, and there's an open source code repo for this.
Okay. Hey everybody. I've been doing Elixir for 6, 7 years. And for the last couple months, I've just been playing around with machine learning AI because it's getting a lot of hype. That's what this talk about. It's about Elixir, using Elixir to do some machine learning. It's not as powerful as I guess Python is, but you can get a lot of interesting things done. To start, I was in the middle of writing a dominoes game. I'm hoping you can see my screen. Um,
It's good. Yeah, you look
and
good.
and As I was writing the dominoes game, I realized that it's adding machine learning to this is going to be really difficult because dominoes is, if you've ever played it, there's a lot of strategy there. It's very complicated. So in this case, if it would depend, like if I have all of the fours in my possession, then I would play differently than if I had only one four. It's a lot more complicated to do at a machine learning too. So I decided to do something simpler, which is do machine learning with tic-tac-toe. But it's not but it's tic-tac-toe with a twist. So it only keeps track of the last three moves you've had. Uh, so let me do a quick show and tell of the game real quick. Uh, so if you can still see my screen, um, so as I try and add a fourth piece, that the one with the underscore is about to disappear. Um, just to give it a little something different than the way tic-tac-toe is normally played. Um, and kind of also the idea was that I could maybe have a four-player, have many more players than just two, and try and see if I could extend the two-player AI to extend to multiple players. Um, so that was the idea. Um, Back to the presentation. Um, so there's two libraries. One is Axon, and the other one is it's in progress. It's called Rain. It uses reinforcement learning. So I don't know who's done anything about deep learning or machine learning. Um, but just to explain the difference between reinforcement learning and deep learning, reinforcement learning would be if we were playing a game and you would train it from the first move to the end move. So I would start it with no pieces here, and it would learn from first move, second move, third move, and I would train it uh, with the winning moves from a winning game and it would eventually learn from multiple games. This is how you should play. Um, and that's a work in progress. It's done by Dockyard. Um, so instead, I'm using deep learning with Axon, and then I'm treating this game as a classification problem to try and predict the best move. So to explain classification, um, the the example from Sean Moriarty's book is you would give it images of different animals, so cats, dogs, and then you'd give it a new image and have it predict what kind of animal it is based on the existing training set. So the training set would be fixed, so a fixed set of animals, and the output would be would be one of the animals from that set. Um, so the idea is that I would train it on the shape of the board. Since there's only 9 places to go, 3 X's, 3 O's, and 3 blank spots, there shouldn't be that many combinations to deal with. Um, so I could get away with treating it as a classification problem. A larger game like chess or Go, where there could be whatever millions of moves and uh, lots of open positions and lots of different types of pieces that can go anywhere. That's a lot more complicated. It wouldn't work as a classification problem, but all of these, the X's and O's are basically equivalent. They all do the same thing, so it's a lot simpler to do this as a classification problem. And just kind of to briefly give an overview of deep learning and neural networks. Um, so the input would be the current shape of the board. So in this case, it would be 2 O's on the left and 3 X's on the right. Um, and so I would map this shape of this board to a matrix, to a one-dimensional array, basically. And then there would be these hidden layers, and then there would be some math applied from the input to the hidden layers, and then that output would choose which space the next move should go to. So in this case, the input is this board on the left, and then the best move would be the X, the top right position for X. Um, um, and if there are any questions, feel free to ask me or interrupt me if it doesn't make sense. Um, uh, so to start, to get all of the positions. So this is how I map the shape of the board to what would be the input for Axon. So the current position, so I map this board to be an array of from 0 to 8, so 0, 1, 2, 3, 4, 5, 6, 7, 8. So then I have this tuple here. Uh, this is my training data. So I have this tuple, the first item is an array where it would be 0, 0, 0 means nothing's taken. 1, 1 would be player 1, player 1, player 2 goes here, another player 1, player 2, player 2. And then this second array would be the oldest move, the piece that's about to be removed from the board. So in this case, on the next move for player 1, the third item 0, 1, 2, 3, this item would be removed for player 1, and the fifth item in the array would be removed for player 2 on the next move. So and then it would be the best move, or if you're looking at the logging data, then this would be the move that's been played by the player. So in this case, the next move would be here by player 2. Or by player 1 or player 2. It's actually, sorry. And also these tuple, this data is always from the player 1's point of view. So even if it's players 2, I'll go into the data a little bit later, but for my logging purposes and to make it easier to handle the machine learning, I'm mapping all of the inputs to be from as if player 1 was about to make the move. So in this case, player 1 would play 0, 1, 2 in this position for the win. And then to map that data to something that's a little bit better for for deep learning purposes, I'm using one-hot encoding, which means I'm converting those values of 0, 1, 2 into just zeros and ones, because it's a little bit easier for the deep learning to understand uh, what, or it's easier for it to find a pattern when there's only zeros and ones. Because it doesn't understand, like in this case, this is a game, so it doesn't understand that does 0, 1, 2, does one mean that is it's a player, or does two mean that it's twice as good as one? Like it's very confusing to the machine learning. So it's a little bit easier if you just translate it to zeros and ones. So I'm mapping this board to a one hot encoding. Uh, so this is how I map these. This is how I map this board position to this one hot encoding. So a zero, which is the blank empty, a not taken space would be 0, 1, 0. So that's this. The next is zero, also not taken. This is also not taken. And then I get a 1, 0, 0. So that means that player one is here. Oh, sorry. This is a underscore. This means that this piece is about to get removed and this piece is about to get removed. So that's this 0, 0, 1, 0. So that's player one right here. This is also an underscore. It's about to get removed. So it's a 1,000 and so on and so forth. Does this make sense to everyone? I can't see the faces, but I'm assuming if you have questions, again, feel free to ask.
Yeah, it makes sense.
Uh, so that's the one hot encoding. And then also I have to deal with data augmentation. So these are all equivalents. I have to train the data. So in the example in the book, when he's training the uh, different types of animals, he rotates the images so that you're not just training it uh, from the same point of view. You can get it from rotated to the left. You can get an upside down picture. So you need that variety in order to train the image, to train the algorithm to understand that cats are all the same, whether they're upside down or right side up. And the same thing I'm doing for for the grid position or for the board position. So these are all equivalent board positions. So this is the original board position, and this is the mirror image from left to right. This is the rotation of 90 degrees. So I'm rotating it. And this is mirror image top down. This is uh, rotating it and mirror image. And then this is mirror image and then up, down rotation. So I'm basically I have to train it on, these are all the different types of shapes. These are equivalent types of shapes. So when you make the next move, understand that these are all equivalent. And then when it sees it, it should know that what the best move should be. So going on to the training. So the initial idea was to have it play itself and see how it would fare. But because of the way the game is designed, the variation of tic-tac-toe that I'm using, uh, these games can go on forever, and they did. Um, and so I had to limit the games to 50 moves. And nothing was really learned because these games never ended for the most part. Um, so then the next best idea was to uh, write a separate opponent that would have uh, simple choices. So the opening move, it would take the center if it's there. Uh, if it happened to be later on in the game and it could see go for the win, then go for the win. Else, try and block the opponent if it's there. Otherwise, just play random. Um, and uh, this created too much data. I'm trying to remember why I said this. I'll get back to that. It'll come back to me. Um, so then, oh yes, but actually, because the training data got so large that it kind of became the game for games that would go on for 50 moves. It would became so much training data that it was hard to um, train a good model. Like it just took way too long to train the model to do anything useful. Um, so then I decided to have the same idea, but decided to split between manual training and then the automated training with the simple opponent. So I split the game into three stages, openings, blocks, and winning. Um, I would manually train it on the opening and blocking moves, and I'll show you the training data later. Um, and then the winning moves, which is really anything after the first opening and blocking is basically the first six moves. And then after that is I'm using the moves from the simple opponent, the simple CPU. Uh, and then I could ignore a lot of those 50 move games. I just really cared about the last couple moves. What were the winning moves for that simple CPU? Um, and then I could ignore, for this specific game, I could ignore I didn't have it play itself. I didn't have the uh, trained AI against the simple CPU. I would just use the simple CPU against itself, and then just take the last couple moves. Because it seemed to be better than I would get more variety in moves because of the randomness that was applied. I would get more variety and I could get guaranteed winning moves from that. Okay, so now I'll show you a bit of the code and a bit of the gameplay. Um, so for the training data, I don't know if you can see the code. If not, you know.
Yeah, can you make it a bit bigger? That's good. Yeah.
I can use dark mode if also if that helps.
I think this is
Um,
good.
Yeah, I think
uh,
white is fine, thanks.
um, so I broke these just for my ease of use. I split up into move one, move two, move three, etc. into the first six moves. Um, so again, going back, actually, it's probably easier if I show you the in ASCII art form. So this is just the training data for move one. It's basically take the center. If you have the first move, take center. The zeros means nothing's been taken. There's nothing about to disappear. So take the fourth item in the array, which is the center space. Keep it simple. And then I'll show you move two. Move two is take if the taker, if the second, if the oh, sorry. So this would be if the opponent has taken the corner, and remember, this is always from player one's point of view. So if the other opponent has taken the corner, then take the center. And again, same for move the second for this variation. If the opponent has taken the side position, take the center. And this is the move that if the opponent has taken the center space, then take the side. Uh, so this is take the center's taken, nothing's about to disappear, take the side. And because of the variations that I'm adding on into the training data that I talked about, it'll automatically rotate. So it'll train with the player two has taken this corner, all of the corners, but still take the center. So no matter if opponent has taken any of the sides, just take the center as the second move. And then so on and so forth for all these moves. So I'll just go into further down the line, move number 5. So this was where I start getting into a mix of so the way I'm kind of shaping this game is it's take the center square and then take the side if center square has been taken, And because of that, this game kind of has uh, the same the AI will kind of start the same type of way every time, because I limited the number of shapes that it's training on. So just to take move 5, uh, more variations, but let me make this a little bigger. Uh, so again, it's basically, this is more into, I get into blocking. So it's, or actually, sorry, this is a combination of blocking and winning. So in this case, if there's a winning move, take it. Again, this is a winning diagonal. This is winning uh, down the middle. Again, these are all variations of, these look similar, but this is if the opponent has taken the corners, and this is all similar types of stuff. Just basically take the winning move if you see it. I don't know if I have any blocking moves here. Um, I don't think, I guess, oh yeah, actually, here's a blocking move. So the opponent can win here. So if it happens to see that, uh, block it. And then this would be the same thing probably for move 6. Um, any questions on that so far? So this is all the manual training data that's happened. And then after move 6, I get into the uh, automated training data. So this is a lot. So I'll just take the first couple. Um, so in this case, so that it makes sense, so we don't have to look at that. The apostrophes means that this piece is about to disappear. So you can see the centerpiece is about to disappear, that piece. So in this case, the winning move would be for one would be to take this top corner. This piece is about to appear. This is about to disappear. So just take the corner. Again, same for that. And this is a blocking move, and actually it's a winning move and a blocking move. Uh, and if I take, let's get some random data in here. Let me see if I can just get a blocking move. And sometimes it's not a winning move or a blocking move. Uh, it's a setup move to be the win. Let me see if I can figure out this case. So in this case, this is neither a winning move or a blocking move. Um, but if player 1 takes this spot, it knows that ooh, sorry. See if I can undo the damage that I've done. Find another similar about to win move. Yeah, so in this case, so this is about to win. So this is neither a winning move nor a blocking move. Um, the side piece is about to disappear for player 2. So player 1's best move is to take the center square. Uh, player 2 can do whatever they want. And then this side piece will disappear, and then player 1 can take this spot. Um, so it's learning basically the last couple moves. Setup moves is really what this training, the automated training data is about. It's winning moves, blocking moves, and setup moves. And I could have added more historical data. I chose not to. I don't think it would add anything to it. Possibly the second, if I add, so there's 3 pieces and I could add all 3 in order, the historical moves in order for all 3 pieces, but I'm not sure. Maybe the second move that's about, so I add another array and say this is the 2 moves from now, these pieces will disappear. That might help. I'm not sure it would help so much that it would make the gameplay that much better. Um, but I could have done it. I just chose not to. Um, And then before, let me just get into the model quickly, a little bit of uh, wonkiness. So this is the model for the game. So it's basically taking it's converting this it's creating the array, preparing it for the deep learning to happen. So this is man, that's annoying. So this is the input. So if you go back to let me go back to the presentation real quick. So if I'm mapping this image to this code, the input is converting this grid to this one-dimensional array. So that's this. And then, so this is really a prep. This isn't the input. This is just prepping the Axon to handle that. So this is the input. I have two hidden layers, an activation layer. It doesn't really map. There should be an extra hidden layer for this, but so there should be three hidden layers and then an output. Um, training, training is training. But I'm basically taking the model that was created here. This is the model. Um, and sorry. And uh, this is the data. This is the training. This is the state that has been trained. This is the model. The model is basically a function. So it's not really, don't think of it like a React model where it's a state. The model is a function. And then the state is the training state. And then this data is the input data. So I'm basically giving it all three things, and then it's going to come back with a prediction. So how do I get back? So if I go here, so you can see that this is the prediction. It's basically giving weights to every position on the board. So these are all the positions. So it's a tuple. The first part of the tuple is the weight, and the second part is the position. So it's saying position 4 has the greatest weight. And it's going to give a weight for all the positions, regardless of whether they're valid or not. But it's saying that position 4 is the best move. And then if I couple moves down the line. Let me just let it win real quick. So it knew, so yeah, so you could see that the best move is position 6, but it gave me give me weights for every position on the board. And what else is there? Any questions? I think that's basically it. And also, so I said that I wanted to try and have this work for 4 players. I don't think that's gonna happen because I don't think there's a strategy. I think this is just chaos. This is kind of just random moving around. So I don't think uh, the the model for a 2-player game is going to work for a 4-player game. I'd have to, yeah, basically this is just kind of random. This is kind of, you're just hoping that the other person messes up. There's no real strategy here. And of course, then if you try this, if you try it locally, this 4-player game is using the simple CPU for all of the players except for mine. So it's me versus 3 other simple CPUs. The 2-player is the only one that has the trained AI.
I do have a question. Is related like how many like why do you choose 3 models? What is the reason behind that? Or I know 3 models, no 3 layers.
Um, uh, I think I tried one, so it's kind of just trial and error. I tried one. So the way I trained it, or sorry, so let me step back a little bit. In the book, when he's training the images to see if there's cats and dogs, um, he he has this fixed set of images and he's taking a subset and training it with that data and then using that rest of the subset to test the accuracy. In my case, I'm having it play against the simple CPU, so I'm using the trained CPU playing against the simple CPU, and the reason I have three is mostly just because it worked. I tried one and it was okay. Two gave me better performance, and three was kind of uh, the happy medium. Like it wasn't too slow to train, and it was giving me good enough performance where um, I didn't have to wait forever for this to start. Yeah, so it's just basically just trial and error. So it would win like 65% of the time.
Got you. I'm not very familiar with machine learning, really, so I
Mhm.
don't know what is like ReLU 6 or softmax or activation. Like, what's the meaning of those arguments in the dance?
So those are different types of hidden, we'll say different ways uh, okay, so let me just go into a different slide. So I stole the slide from the MIT course. Can't show. Can I just go full screen? Yes. Uh, so without the activation functions, uh, the you could only really learn to detect a linear split between. So if you wanted to split the data between, let's imagine there's red data, there's green dots, red dots, green dots, and you want to find a way to split the data into two different halves, two different groups. Without the activation functions, you could only use a straight line. And so what the activation functions do, it lets you it introduces nonlinearities in order to discover a better function that can split the data into two groups or n groups, however many groups you have. Um, so so you have different activation functions like ReLU 6. They're kind of it's hard to get without going into deep learning. There are kind of different ways to add non-linearities. It's kind of like you have to. It's an art kind of to figure out which. It's part art and part you need a PhD in order to figure out what these activation functions how they really work. So for me, it was kind of just I tried a couple of them, uh, and these are the ones that give me the best uh, balance between performance and accuracy. Um, it doesn't really answer your question because it's kind of beyond my understanding of them, but there are a
It
couple of
does. It
different,
does. It does.
uh,
I do that every day with things. Poke and
yeah,
see how it works.
yeah. But yeah, you basically have a couple of choices between different activation functions, and you kind of find what works for your specific problem and for your specific data set. Um,
Thank you.
Nice. I'm just gonna stop the recording really quick. We can keep doing the QA.